Okay, good morning, everyone. Let's dive right in just to get reoriented as to where we are and where we are going. Undergraduates, you are going to be tackling assignment 5 this week, if you haven't already, which is motors. Couple notes about motors. We ended last time talking about the little Kepler robot that was running around on the top of a table. That robot has wheels. Your robot has quote-unquote legs. Motor neurons send commands to motors, and motors interpret the numbers coming from the motor neurons in different ways. In these programming assignments, the number coming from the motor neuron to the motor is interpreting that as a desired angle, theta. That's the angle that the motor neuron wants the joint to get to. When we jump back to talking about the Kepler this morning, that Kepler has motor neurons inside it as well. Those motor neurons are also sending commands to the motors, but those motors are attached to wheels. Those motors are going to interpret the values they get from the motor neurons as desired angular velocities, theta per second. Yeah. So motor neurons, all they do is send numbers to motors. The neurons don't really care what those numbers mean. As we continue on in this course and we look at lots of different legged robots and wheeled robots and wegged robots, which are combinations of legs and wheels, the number that's being sent from the motor neuron to the motor is being interpreted differently. Just wanted to point that out now for the undergraduates that are tackling the motors assignment. Okay. Any questions about A1 through A5? So far, so good? Okay. Graduate students, you have reached the end, or at least the end of the beginning. You are going to be tackling assignment 9 and assignment 10 this week, which, again, if you haven't got there yet, in assignment 9, you are going to be implementing 3 different evolutionary algorithms. And they're arguably so simple, they're not really even evolutionary algorithms yet. The first of the 3 that you're going to be implementing is random search, dropping points at random places on the fitness landscape. Once you've implemented that, you're going to go and implement the hill climber. The hill climber drops a random single point somewhere in a fitness landscape. That parent produces a child. If the child lands at some place in the fitness landscape that's higher than the parent, meaning the child has a higher fitness than the parent is deleted, the child becomes the new parent, and the hill climber, as the name implies, starts to climb its local hill. As we saw when we talked about evolutionary algorithms a short while back, the hill climber can get stuck at local maxima or local minimum, depending on whether we're trying to get to the bottom of hills or the top of hills. So the third and final, this is starting to look like an evolutionary algorithm that you're going to implement, is the parallel hill climber. Drop a whole bunch of parents at random places on the fitness landscape, and then execute the hill climber algorithm in parallel at all those points. The parallel hill climber is starting to look like an evolutionary algorithm because at least we're dealing with a population of potential solutions to our problem. That's assignment 9. Assignment 10, you're going to be throwing away this minimal 3-link 2-joint robot that you've been working with so far, and instead switch to a 9-link 8-joint robot that's got a main body, 4 upper legs, and 4 lower legs. For pretty much anything you're going to be creating in the PyBullet physics engine, whenever you have n links, in this case 9 links, you always have 8 joints, n-1 joints, right? Joints connect pairs of links together. Okay, as you build the quadruped in assignment 10, I highly recommend you draw it with pen and paper or annotate on a tablet. However you do it, I would suggest you draw it out first. Get all the coordinates, the positions of all the links and joints straight in your head. You're going to be juggling a lot of different absolute and relative coordinates. So if you're still shaking on that concept, go back and review when and where to use absolute and relative coordinates. And I suggest do not add all 9 links and joints at once. It's a little confusing. Add one link, one joint at a time. Make sure everything's working as you expect it to. Add another link, a joint, and on you go. And at the end of assignment 10, you will have a relatively complicated robot with a relatively complicated neural network controller in it and a parallel hill climber that's wrapped around the whole thing that's going to search for neural controllers for your quadruped to get it to run along the virtual ground as quickly as possible. The end of the beginning. So far, so good? Okay. Next week for the graduate students, you're going to be going all the way back to the beginning and doing everything again, but in a differentiable simulator. And I will say a few words about differentiable simulation in class Tuesday morning when we assign the first of the 10 differentiable assignments to the grad students. But I'm just going to speak very briefly about differentiable simulation, and we will come back and talk about differentiable simulation and differentiable robots at the end of the course. Okay? A little bit of orientation. Any questions about any of that? Okay, I have not dropped a link to the first of the 10 differentiable assignments yet, because I haven't written it yet. I am madly trying to run ahead of all of you, so it'll be ready by next Tuesday morning. Okay, all right. If there's no questions about that, back to our lecture material. We're working our way through, not tools of the trade, we're working our way through this third segment of the course, looking at the admittedly brief history of evolutionary robotics. This particular branch of robotics only started in the early 90s, so we don't have to go back very far. We were partway through our discussion of actually the first 2 experiments that were reported in the literature back in the mid-90s. We'll go back and start talking about those in a moment. We will finish that discussion today, and then we will start in on lecture 8, where we're going to take a little bit of a digression and talk about a particular kind of neural network. That's the N and N in CTRNNs. CTRNNs were invented in the mid-90s, and they were used for some minimal cognition experiments, which we'll probably talk about later this week or into next week. Okay, that's where we are, where we're going. Okay, so back to the mid-90s and the early days, the very early days of evolutionary robotics. This was arguably the first reported evolutionary robotics experiment where, as we saw last time, it involves this little hockey puck-sized Kepler robot with 2 wheels. Just to remind you, it's got 6 proximity sensors on the front, 2 proximity sensors in the back, 2 motorized wheels. I just erased it. The 2 motor neurons here are sending desired angular velocities to the wheels, which can cause the wheels to rotate backwards, stay still, or rotate forward. The 6 proximity sensors, the proximity sensors will report very low values if they see nothing in front of them or something far off, and each proximity sensor starts to fire more strongly as that proximity sensor approaches some object that proximity sensor is facing. Okay. I ended last time by challenging you to think up a fitness function. We're going to use phi for our fitness function here. We're going to try and write down a function here of these 10 variables, some combination of these 10 variables. And we want to write down a function so that whatever the values of these 10 variables are, the function evaluates to 0 or near 0 if the robot is doing the worst possible thing. And this fitness function, when fed these 10 numbers, should evaluate to a number very close to 1 if this robot is doing close to or very well at whatever we want the robot to do, which in this case is to drive around and around this track as quickly as possible. Let's go. What did you come up with?
I'm assuming that 1 through 6 is the first 6 sensors that are on the front of the robot, and 7 and 8 are on the back.
We can assume that. Proximity sensors 1 through 6 are on the front, and 7 and 8 are on the back.
So you'd have VL, and then have it be multiplied by VR to make sure that they're both going at like a sort of equal distance for you to get 1, and then VL should be like having 1, 2, and 3 subtracted by 4, 5, and 6 to get like what the true value of VL should be, and then have the opposite for VR.
Or when you say 1, 2, 3, you're talking about the proximity sensors now?
Yeah.
Okay, let's hold off on the proximity sensors for a moment. This is a good start. Let's incrementally build up this fitness function. I want you to run this in your head. We don't have a Kepra here, so we can't try it out. So if we drop a neural network controller into our Kepra here, we drop in weights for all of these synapses, and the resulting wheels don't rotate at all, for example. So VL and VR are near 0. The robot is staying still, and phi is evaluating to a value near 0. So a pretty good start, right? The wheels don't turn, the robot isn't moving, it's not doing what we want, and the fitness function correctly says, yes, this set of synaptic weights is not causing the robot to do what we want. Let's assuming VL and VR are both spinning forward very quickly, and the robot takes off and starts driving in a straight line. It's a good start. This is going to evaluate to some value, maybe not 1, but at least above 0. It's doing the right thing. What about the left wheel spinning back and the right wheel spinning forward? And the robot is turning counterclockwise.
Isn't that going to give you a negative value on
A negative value. So not quite what we wanted here, but at least we're in the right ballpark, right? Higher values, more positive values are rewarding controllers that cause the robot to move forward very quickly, or both wheels turning backwards very quickly. Nice idea to multiply these together, because if they're both negative and the robot is reversing, there's nothing here that says the robot can't drive backwards through the maze. That's okay. That would also give us a high value of phi, so pretty good.
Could you maybe divide it by VL times VR plus the summation of the proximity sensors?
Say that again. You wanted to divide it by something?
Dividing it by VL VR, so that way it's like always, so it can't be above 0, and then in the denominator.
Wait, so you want to put VLVR on the denominator?
Keep that as
Okay.
the numerator, but then divide it by the sum of that term plus the summation of the proximity sensors.
The summation of the proximity sensors. Yeah.
So then you're trying to like minimize the number of sensors that are on at a given point, so you're trying not to run into stuff.
Okay, so let's iterate over all 8 proximity sensors.
And then just adding the VL VR term, that way if you have none, that it's not like infinity.
Okay, all right, so J is going to iterate over 1 through 8. So this is the value of the jth proximity sensor. I was not a good choice for proximity sensor, but there you go. All right, apologies for my notation here. So we're going to sum up all of these, and then you want to also add the product again? Did you say?
That way if all those terms were 0, you're not dividing by 0.
Fair enough. Okay. Can you run this fitness function in your head? We drop some random set of synaptic weights onto the Kepra, and let's imagine that the Kepra takes off in a straight line. VL and VR are both positive. Both wheels are rotating forward, so the robot starts to move. Let's say this is forward. Hard to tell from this grainy 1990s photo which direction it's actually pointing in, but let's assume this is the front of the robot and it starts driving forward. As it starts to drive forward, what's happening to the 6 proximity sensors on the front of the robot? Maybe not all 8, but for the majority of the 8 proximity sensors, what's happening as it starts to move forward?
The values are changing.
They're the values of the 6 on the front changing how?
Well, we're getting closer to a wall, so they're gonna have higher values.
They're going to start to increase. So the value down here on the denominator is starting to increase, which is pulling the whole value of phi downward, which is good. That's the intuition that we want.
What if you,
Go ahead.
like, if you spin in a circle in the middle with no walls, wouldn't it just be 1?
Yeah.
So if this spins in a circle, we've got one of the wheels with a negative angular velocity and the other wheel with a positive angular velocity. So they're canceling out, right?
Well, and then you put it over itself.
So we've got 0 on the numerator. We've got 0 down here, and it's spinning in place, so I don't know what the proximity sensors are doing. It's starting kind of near this wall, so maybe they're kind of intermediate values, kind of hard to say.
I was saying, like, what if it's near 0, but you still have, like, the same number on the top and bottom?
If the proximity sensors are firing near 0, you're saying?
Like, if the proximity sensors are near 0, and then VL, VR are, like, they're not moving the robot around.
Yep.
They're, like, moving enough that they're not 0.
Okay.
So you just have, then it would just be 1.
Maybe
Right?
instead
I would
of,
say it'd be, like, the best.
Okay, possibly.
maybe instead of adding VLVR in the body, we just add 1 because that would be the like maximum value of that. That way it wouldn't cancel out its signs. And
Okay, maybe a little bit better. If you're not able to follow what kind of behavior this is selecting for to run this in your head, that's okay. The main message I want you to take away from our little discussion here this morning is that it's not easy to actually write down a fitness function and give it to the evolutionary algorithm. This is arguably one of the simplest evolutionary robotics experiments we're going to see in this course. As we keep going, things are going to get more complicated. We're going to have robots with more motors, more sensors. We're going to want them to exhibit more complex behavior, which means there's more possibility of perverse instantiation. There's more ways for this thing to do the wrong thing, right? We started our discussion of the Kepler about thinking about this, which meant one perfectly valid solution is this, right? So we've got to multiply them to guard against that particular kind of perverse instantiation. It's tricky. Okay. Here's what the investigators of this experiment came up with, and we're going to walk our way through this. First thing to notice about the fitness function is it's the product of 3 terms. 1, 2, 3, and we're going to talk about these 3 terms in turn. Let's start with the first one. Uppercase V, this first term is actually a sum of the absolute values of the velocities of the wheels. And remember that the wheels can the wheels can rotate at any velocity in the range of minus 0.5 theta per second up to plus 0.5 theta per second. So by summing the absolute values of these, we can guarantee that this particular term ranges between 0 and 1. As you all have already identified, if we had just, I can't cover up this term, but if we had just plugged in V and not these other terms, our robot is still vulnerable to perverse instantiation, right? This spinning in place where one wheel is rotating at minus 0.5 and the other wheel is rotating at plus 0.5, that would still max out this particular term. I don't know, but I'm guessing the researchers probably did this and ran it on the robot and saw as evolution proceeded that the robot evolved to spin in place faster and faster. That's my guess. So they probably went back to maybe literally the whiteboard and multiplied it by 1 minus the square root of delta V. So what does delta V do? It takes the difference between the magnitude of the 2 velocities. We're going to see a lot of double and triple negatives in fitness functions, so we've got to lean into this. Here we go. So what values of VL and VR minimize delta V? For both?
Um,
What values of VL and VR will minimize delta V here? Just delta V.
Anything that's close together.
Anything that's close together, right? The more similar VL and VR are to each other, the smaller delta V, the smaller the delta between VL and VR. If we go back to this term, forget the square root for a moment, they're taking 1 minus delta V. What maximizes 1 minus delta V? What maximizes 1 minus delta V? When VL and VR are the same. Again, apologies, lots of double negatives here, right? So a set of synaptic weights, some set of synaptic weights dropped into the robot and the robot starts performing, a set of synaptic weights can maximize 1 minus delta V by getting both wheels to turn as similarly as possible. And that same set of synaptic weights can maximize V if they're spinning backwards together really fast or forward together really fast. So far, so good?
For just like capital V, is 0 pointing towards 1 talking about like the limit or like the range of that?
Yes, I'm sorry. Again, this is probably not great notation. This is me just showing you what the range of this particular term is. Yeah. They were trying in this case to come up with a fitness function that ranges between 0 and 1. It's maybe not strictly necessary, but just in this first experiment, they were trying to cross all their T's and dot all their I's. Okay. All right. What about, why are they taking the square root of delta V? This is kind of a detail, but maybe worth pointing out. I'm giving you a very strong hint here. Why didn't they just create a second term that was 1 minus delta V? Why 1 minus the square root of delta V?
When you're trying to find like the diagonal distance, then you need to find the square root of the two variables. And if you're moving on like a two-dimensional plane, then you need to be computing it in relation to like the Pythagorean distance?
Not quite. So let's have a look at the square root of delta V. So let's put delta V along the horizontal axis. Let's imagine that we're going to start the evolutionary process. We're going to start dropping sets of random synaptic weights into the robot. Most set of random synaptic weights that you drop into this robot are going to probably cause it to fidget and move a little bit, but definitely not race around the track. So there's probably going to be small differences in delta V. The wheels are turning a little bit. They're a little bit different. Let's imagine we're running the hill climber on the set of synaptic weights. So we have one set of synaptic weights. We drop it into the Kepra. The Kepra kind of jiggles in place. And whatever else it does, there's a relatively small difference in the angular velocity of the two wheels. The hill climber takes that single vector of synaptic weights, makes a copy of those synaptic weights to make the child genotype, and when it copies the parent to create the child, it makes a slight change to one or a couple of the synaptic weights. So now the child is all those child synaptic weights. We drop them into the Kepra and we evaluate the Kepra a second time, and it also kind of spasms and jiggles around a little bit, but maybe there's a little bit more of a difference between the speeds of the two wheels. So we've moved by chance from the parent to the child to have a slightly larger delta V. Tell me about the square root of delta V. What happens as we start to move to the right and we have robots that are exhibiting a greater difference between the angular velocity of the left wheel and the right wheel? What does the square root function look like? So a child that exhibits slightly more delta V than the parent is going to have a much larger value of the square root of delta V. And we're taking 1 minus this. This term is a punishment term. 1 minus. The bigger this is, the smaller, the closer to 0 this overall second term is. So the square root, they added the square root in to exert greater punishment on delta V if delta V starts to creep up in children compared to their parents. Everybody see that? Okay, so we're going to see a lot of fitness functions throughout this course, and that's why we're spending quite a bit of time talking about this first one. This one has 3 terms in it. These various terms are rewarding or punishing for certain aspects of the behavior. This term is rewarding for speed. Turn the wheels, don't sit still. This term is punishing for turning, right? Keep the speed of the wheels as similar as possible. They added this extra square root to extra punish for turning. It doesn't say in the paper if you go back and read it, but my guess is when they started dropping sets of synaptic weights onto this Keppra and watching one behavior after another, most of those behaviors, the robot was probably doing a lot of this. So they went back, I'm guessing, and added square root to root out, get rid of that behavior as quickly as possible. They're exerting more or stricter punishment for doing more of a bad thing. Everybody see that? Okay. Given that, tell me about the third term. What is the third term? Is it rewarding or punishing?
I think it's another punishment term for getting too close to walls.
It's punishing for getting too close to walls. The clue that it's a punishment is it's 1 minus something. So it's probably this term is probably trying to minimize this something, this I.
And also, if I'm not wrong, it's punishing less than the other punishment terms. It's a linear function. So
It is punishing less. Yeah, they did not apply a square root to this. Okay. Terrible notation here. We've got 1 minus I. So let's go and have a look at I. We won't actually write out the equation for this, but at every time step that the Keppra is running around on the tabletop in this maze, they look at all 8 of the proximity sensor values. And remember that the proximity sensors can report a floating point number anywhere between 0 and 1. So they're looking at all of them, and they're looking for the highest number among those 8 proximity values at that time step. They hold on to that maximum value. The robot moves again a little bit, and they're recording all these sensor values. They look at the new set of 8 proximity values, and if there's a new value within that set of 8 that's even higher than the maximum recorded value so far, they throw away that value and hold on to that one. So among all 8 proximity values, over the lifetime of this robot's behavior, they're looking for the maximum value of any proximity sensor. Why? Why did they do that? Why not just take the average?
Because the maximum value would be the one it's closest to, and so it makes sense to pay attention to that so you don't bump into the wall you're closest to.
Absolutely, right? So the robot might actually stay still for quite a while, and then right towards the end of the evaluation period, it suddenly takes over and hits the wall, right? If we took the average of all the proximity sensors over those, let's say 10 seconds that we evaluated the Keppra, the average value of the proximity sensors would actually maybe be pretty good, right? This robot is only as good as its worst proximity value. What's the closest it ever gets to a wall or potentially hits the wall? So generally speaking, we're trying to minimize the values of the proximity sensors, stay away from the walls, and go really fast, and make sure your wheels turn at as similar values as possible. Multiply all those three together. And I'll show you the experiments on the next slide, but as you can imagine, with all of this lead up, they ran this experiment. They kept dropping sets of synaptic weights over and over and over again into this little hockey puck. And eventually, they started to get sets of synaptic weights that yielded motor, and sensor values, which when combined into phi, started to produce values of phi closer and closer and closer to 1. What behavior do you think was doing that? What was the robot actually doing? Or getting better at doing as phi started to approach 1 over evolutionary time?
Driving around pretty fast without hitting anything.
Driving around pretty fast in the maze. This is the mid-90s, pre-YouTube era, so I'm afraid no fancy videos. We'll see lots of fancy videos later, I promise. Here was their attempt to show you what the best set of synaptic weights did. They ran their evolutionary algorithm for almost 3 days, and at the end of those 3 days, they had a particular genotype that, when supplied to the robot, produced this behavior. What are you looking at? Each one of these little cross stitches is the center of that short line segment is representing where the robot is, and the angle of that little line segment is indicating the direction that the robot was pointing in. Everybody see that? And each one of these little ticks is representing changes in the position of the robot and the position of its heading. How did the robot do? Did the robot do the best? Is this the best it could have possibly done? Maybe. Probably not. You can sort of see from some of the little wiggles and kinks in the trajectory that even though we don't know what the optimal solution is, we can be pretty sure it's not the best. Biological evolution and evolutionary algorithms are satisficers, not optimizers. We're never guaranteed to get the best behavior. We hope that for most applications, really good or pretty good is good enough. Questions? Okay. All right. So we haven't really talked about the evolutionary algorithm itself. They didn't run a parallel hill climber, but it was something like a parallel hill climber. They had a population of vectors. They took each vector and dropped those random synaptic weights onto the Kepra robot, evaluated the Kepra for about 10 or 20 seconds. Somebody reached in, grabbed the Kepra, put it back to the starting position in the maze. Somebody else on some desktop hit enter, which downloaded the next vector or set of synaptic weights onto the Kepra. It ran around for 20 seconds, reset the Kepra, download the next one. The first generation, which contained a whole bunch of sets of random synaptic weights, took 40 minutes to run. After they had evaluated each genotype, each set of random synaptic weights, they applied phi to each of those vectors, and vectors that suffered a low value of phi were deleted, and those vectors that enjoyed a high value of phi produced randomly modified copies of themselves, and those new vectors were again downloaded on the Kepra and over again for another 99 generations. Question? Yeah, it's not specified here. I don't actually remember. You'd have to go back and look at the paper. Let's say 100. I'm not quite sure, right? So 100 random vectors, that means you got to evaluate the physical Kepra 100 times. So 10, 20 seconds of evaluation 100 times, plus half a minute or a minute to reset the Kepra, press enter, download, blah, 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 with mid-90s technology. And all of that added up to about 40 minutes of real time in the real world. No physics engine here, real time. Yeah? Okay. They sat there and did this for 66 hours, not all at once. They took a break, but it took them a total of a little less than 3 days to do one trial of an evolutionary algorithm, and they got this at the end of 3 days of effort. Yeah? Okay, again, I apologize for the quality of these images. What you should be able to see, and you might not be able to see this from the back of the room, is on the horizontal axis here, we have evolutionary time. Here's generation 0 here, and here's generation 100 over here. And on the vertical axis, it says fitness, but they're plotting phi. And remember that phi in theory can range between 0 and 1. And if you squint very carefully, you'll see the top of the vertical axis here is 0.3. This lower curve here, this is averaging the value of phi for all the individuals in the population at that generation. So among all the random neural network brains for the robot in generation 0, they cause the robot to fidget and not move very much, or maybe bump into the wall, and all of them suffered a value of phi very, very close to 0. Not surprising, these are random behaviors. This upper curve reports the best individual in the population at that point in evolutionary time. So among all these sets of random synaptic weights, there was one vector, one set of random synaptic weights that caused the robot to actually achieve a value of phi of about 0.005. Not great, but better than the average. As evolutionary time proceeded, that particular parent started to produce children and children of those children and so on, and the average behavior of all the sets of synaptic weights in the population started to rise over evolutionary time, and the best in the population also started to get better until they reached this particular set of synaptic weights up here, which achieved a phi of 0.22, 0.23, which produced this behavior. A lot of effort for not a lot of gain, but this is the mid-90s, and this was one of the first demonstrations of automated design of an automated machine. If you remember back all the way to the beginning of the course, that's the long-term goal of robotics. We want to create a machine that is not remote controlled. It's deciding what to do based on its sensory information. And we don't want to manually program an autonomous machine because it's super hard. So although this is very humble and very simple and took a long time to do, this was a partly automatic. Someone was still reaching in and moving the Kepra and hitting enter on the desktop, but getting there. Automated design of an autonomous machine. So far, so good? Okay. All right. What do you see down here? Again, I apologize. We've got the same horizontal axis down here. This is evolutionary time over here. The solid black line here, the solid black line is reporting the value of uppercase V for the best individual in the population. Uppercase V is the angular velocity of the wheels. So we can see that the solid line started near 0, which means that even for the best individual in the population, the wheels were turning just a tiny little bit, very, very low angular velocity. Over evolutionary time, the evolutionary algorithm started to discover sets of synaptic weights that caused the wheels to turn faster. The dotted line represented here, this is reporting 1 minus the square root of delta V. What's happening to 1 minus delta V, square root of delta V over evolutionary time? It's starting to go down, right? Remember, this is a punishment term. We want to punish this. We're taking 1 minus this, which means we actually want 1 minus the square root of delta V to go up over evolutionary time. But it's not. It's bouncing around quite a bit, and then maybe it sort of evens out at intermediate values. What's going on?
The robot needs to turn to go around the track, so it can't, there needs to be differences.
If it's going to move around through this track, it by necessity has to approach some of the walls. It can't help it, right? The robot can't have its cake and eat it too. It's got to balance displacement. It's got to move and not move in place. And it's got to stay away from the walls. If you look at the solid line and the dotted line, this is evolution trying to strike a balance between what are called antagonistic terms. These two terms, generally making one term better through evolution, causes the other one to be worse, and vice versa. It's trying to strike a balance. Yeah? Our ancestors, as they were evolving to walk around on our hind legs, we were trying to strike a balance between staying upright, not falling down, being able to move relatively quickly with relatively little food in our bellies, and not lose a lot of children to childbirth. Standing upright caused a lot of evolutionary changes to the hip structure of hominids. Evolution had to strike a very, very careful balance between figuring out how to alter hominid physiology so that we could walk upright in an energy efficient manner, not suffer unduly high rates of childbirth. Everything that happens in evolution is always a trade-off between antagonistic pressures. Yeah? That is part of the reason why biological evolution and an evolutionary algorithm is a satisficer, not an optimizer. You can't have your cake and eat it too in the real world. Okay. Dash line, this one's a little bit harder to interpret. Oh, I'm sorry, I misspoke, right? We were talking about the dotted line. This is not staying away from the walls. This is turning. I apologize, I misspoke. This overall term here is punishing big delta V's. But if you're going to move through this maze, you have to turn. And when you turn, you experience an increased delta V. One wheel has to turn faster than the other. I'm sorry, I misspoke. So it's still striking a balance between the solid line, which is go fast, and the dotted line, which is don't turn. Then there's also the dash line, which is also trying to keep the robot away from the walls, and it can't do a perfect job of that. Yeah, it's a bit of a juggling act here. Okay, apologize, I misspoke. Okay, this was their attempt to try and draw, to better show you how evolution is moving through the fitness landscape and striking a balance between these three competing terms. I'm not a big fan of this plot, so we're just going to push on in the interest of time. Okay, so what they wanted to know was how well did they actually do? They put a lot of blood, sweat, and tears into actually evolving this behavior. How good is it? They don't know. They don't know what the optimal is. But the researchers sat down and used a lot of brain power and actually did try and write down weights for all of these synapses that would cause the robot to move through the maze. What did they do? They created a Bratenberg vehicle. What kind of Bratenberg vehicle would you want to put into this Kepera to cause it to race around the maze but stay away from the walls? Coward with the walls, yes. So when the proximity sensors on the front left were firing strongly, meaning the front left of the robot was close to a wall, that should inhibit the contralateral wheel. So something is approaching from the front left, that should cause the right wheel to slow down relative to the left wheel. The left wheel is now spinning faster than the right wheel. The robot should turn to its right, away from that obstacle on its front left. And hopefully if it points up and into the tunnel, into the track, there's less stimulation of the 6 proximity sensors on the front, and it goes forward. That was the best they could come up with. And it does okay at driving around and around the track, but the Bratenberg vehicle has a problem. As it's racing around the track, if it ever starts to head directly into one of the corners, specifically this corner, the robot slows down and grinds to a halt. You can see there's a whole bunch of these cross hatches sitting on top of one another. The robot is facing into the corner and doing this. Why?
It's getting inhibited on both sides.
It's getting inhibited on both sides, right? It's facing into the corner. There's slightly more proximity on the left. Turn to the right. Now there's slightly more proximity on the right. Turn to the left. What they found is when they took their evolved individual and pointed it directly into a corner, it didn't have this problem. It would turn to its left and do a 180 and start heading up the track. Their evolved individual was better than a Bratenberg vehicle. It got stuck less often. That's a strong hint to what's going on among the set of evolved weights. Most of the time, evolution comes up with a set of synaptic weights for our robot, and our robot does something, and it's very hard to have any insight into what exactly those sets of synaptic weights are. In this simple example, we actually can gain a little insight from the nature of the behavior into what the synaptic weights probably are. What's the hint here? What can you, I haven't shown you the actual set of evolved synaptic weights.
Well, we know it turns specifically to its left.
Yep. It doesn't do this jittering in the
And
corner.
We know that in theory, we know that the direction it's moving around the track is counterclockwise at all times.
Yep.
So it's always going to prefer moving to its own left.
That's true. So that's a description of behavior. We're trying to go from behavior, which in this case is just make a 180 when you're pointing directly into a corner, to the sets of synaptic weights.
So the weights have just evolved like asymmetrically?
The weights have evolved to be asymmetric. Whatever the sets of synaptic weights are on one side of the robot, it's different from the sets of synaptic weights on the other side of the robot. The synapses here have probably evolved a little bit of asymmetry on purpose. If you're perfectly symmetric, like a Bratenberg vehicle, that's not necessarily a good thing. An interesting observation. If you look around in nature, including the 20, 30 or so hominids that are in this room right now, we mostly look bilaterally symmetric. The left of you looks like the right side of you. For most purposes, being bilaterally symmetric is a good thing. But there are certain subtle situations where a little bit of asymmetry is actually a good thing. And there are cases of that in nature. And here we see artificial evolution rediscovering that fact, that a little bit of asymmetry is sometimes a good thing.
Did they try the robot in like a different maze?
Great question. If they did, they didn't report it in this paper.
Probably did horribly.
It probably did horribly, and they were probably exhausted after all of this and figured they'd done their due diligence, write it up, and submit it for publication. I would agree. Who knows? They don't say. Okay. Any other questions about this first evolutionary robotics experiment before we move on? Okay. This experiment was conducted in Switzerland in about 93, 94. At the same time, on the other side of the English Channel at the University of Sussex in the UK, this particular experiment was being conducted. So in the history of the field, it's usually these two experiments which are pointed to as the first ones. Which one came first is a matter of argument. Okay, this robot, it looks very, very different from the one we just saw. Here we go. This has become known since as the gantry robot for a very good reason. It's a gantry. These Sussex researchers took a table and a saw and sawed out the actual table to just leave the frame of the table. And then they set this large wheeled trolley on top of the table. This is known as the X trolley. This X trolley can move back and forth, left and right, along the top of the table. On top of this X trolley, they placed a smaller Y trolley that with a wheeled trolley that can move up and down along the spine of the X trolley. So far, so good? Okay. They then dangled, again, they had a tether to a desktop, no Wi-Fi in the mid-90s. Everything's going to run on the desktop computer here. They have a tether and cable, and that cable descends and drops through the center of the little Y trolley and drops down below the table. And at the end of this tether is a camera pointing straight down towards the ground. This is a very crazily designed robot. So far, so good? Okay. The camera is in here. You can't actually see the camera. It's pointing downwards. It's not actually pointing at the ground. It's pointing at a little circular dental mirror, this little circular mirror. This circular mirror is attached to a little motor underneath, and this motor is spinning this dental mirror. This design is getting crazier by the minute. So far, so good? Tell me about this little vertical setup here. It might sound a little bit familiar. We have something that's pointing in a vertical direction, and there's something that's spinning, allowing the robot to look actually horizontally around itself under the table. It's an inverted periscope, right? Like on a submarine, you send something up and you look around. This is just the opposite. Something is pointing downward under the table and looking around at things placed on the floor under the table. What was the point of this crazy machine? I did my master's degree at the University of Sussex in '99, and at this point, the gantry robot had been mothballed. It was 6 years old at this point, but it was still there. And of course, all the students wanted to go over and look at this machine, which should have ended up in a museum. I don't know what actually happened to the gantry robot. Why would serious engineers ever make such a crazy machine? As you can guess, they're going to start to drop sets of synaptic weights onto this robot to control the gantry robot and the spinning motor to cause it to do some desired behavior in and among objects placed underneath the table. Why did they set things up like this? Any idea, Emily? What's that? Of a drone? Okay, maybe. This is long before drones ever existed. Yep.
More like a satellite, like GPS.
Okay, maybe they're trying to prototype some bigger, more serious technology. Turns out that wasn't the reason. There was an actual here and now practical reason for setting things up in this way. It seems odd. What's that? Oh, yeah, maybe this would again approximate some sort of rover moving around.
Is it so that you can just move in X and Y without having to turn?
We're getting closer.
Yeah.
Getting closer to the answer.
Something in a factory?
Some-
Or in a fixed area?
Yeah, okay, so don't think about actual applications. Maybe this particular way of setting things up, no. They're about to run an evolutionary algorithm on this robot. And they set everything up in a particular way to make this easier. In the back corner.
Finding like the shortest distance to point A to point B with objects in the way?
Could be. So we're proposing like what kind of behavior they actually evolved. Doesn't matter what the behavior is. Why set things up in this way?
Well, it's like, it's, as you said, it's like so it can be just highly specifically in like three variables to actually play with.
3 variables, right? So there's the motor controlling the X trolley, a motor controlling the Y trolley, and a motor controlling the spinning dental mirror. Okay, I'm really fishing here. Let's see if I can get it.
Is it literally so the cord wouldn't get tangled?
Now we're getting a lot closer, right? If you think about it, with these 2 trolleys moving around, the cable actually never rotates. We're getting very close to the right answer now. They've made their lives simpler. They don't have to go in and disentangle this cable. The Italian researchers back in Switzerland, they had to go in and untangle the wire over and over and over again.
Yeah, they didn't have to reset everything up.
There it is. Drop a set of synaptic weights onto the gantry robot. The X trolley, the Y trolley starts moving, the dental mirror starts moving. They collect all the data from this moving robot on the desktop. They have some fitness function that computes the value of that set of synaptic weights. They're done after about 20 or 30 seconds of evaluating that neural network controller. They hit one button on the desktop and everything moves back and resets itself without them having to touch the gantry robot. The Sussex researchers were smart. They started to realize what they were getting themselves into if they were going to try and evolve behaviors for this robot. That's why they designed it in this crazy way. Okay. All right, so we just talked about the three motors, something that moves the X trolley back and forth, a second motor that drives the Y trolley back and forth on the X trolley, the Y trolley on top of the X trolley, and a third motor in here that spins the dental mirror. Let's talk about the sensors now. We've got three motors. In this particular gantry robot, there are 7 sensors. Let's go through them. You'll notice there's one additional item they've placed on the bottom of their inverted pendulum, which is just a little plastic disc. Nothing fancy going on here. But as this inverted pendulum is moving, inverted periscope is moving underneath the desk, if that inverted periscope ever bumps anything, this plastic disc will hit that object under the table first, and it will deflect. It'll rotate this whole thing, and there's a little sensor sitting in here which is detecting the angle of deflection of this plastic disc. I won't go into the details, but they basically take the result from that sensor and they turn it into 4 different binary sensor values. Was the robot bumped from the front right? Yes or no. Was the robot bumped from the back right? Yes or no. Same. So we got 4 different sensors. Each of those sensors at any given point in time when the gantry robot is moving, each of those 4 sensors is either going to report 0 or 1. So far, so good? Okay. All right. This is the tricky part. The 5th and 6th and 7th sensor. Pay attention. Here we go. I mentioned that there are 3 motors in the gantry robot. In the evolutionary process we're about to see, the neural network controller of the gantry robot only is able to control the first 2 motors. The neural network controller is only going to drive the 2 trolleys. They're going to set the 3rd motor to a constant angular velocity. That motor is just going to keep spinning constantly. Doesn't matter what the trolleys are doing, which causes the dental mirror to rotate around and around at a constant velocity. And the camera is continuously recording frames, video frames, of what is hitting the dental mirror. So far, so good? So imagine you're in a submarine looking through a periscope upwards, and you keep doing this. Imagine it's probably easier to just take everything that is seen in that 360 view and squash it into one frame that's showing you a complete 360-degree view. So far, so good? That's what the gantry robot did every 1/10 of a second. The camera spun the dental mirror through one 360-degree rotation every 1/10 of a second, and the desktop computer actually stitched this all together into one 360-degree view. So far, so good? Okay. This is mid-90s technology, so they're getting a huge amount of pixel data every 1/10 of a second. It's too much information to feed into a neural network controller at that time. So they added one additional detail, which is inside the set of vectors, inside the vector that encoded the synaptic weight, there were an additional 9 numbers that were tacked on to every set of synaptic weights. So we're talking about the genotype now. A genotype for the gantry robot encoded weights of all the synapses that connected the 7 sensors to the 2 motors, the motors that control the 2 gantry robots, and 9 additional numbers. What do those 9 additional numbers encode? I want you to take those 9 numbers and break them into 3 sets of 3 in your mind. Each triplet of numbers specifies a 2D coordinate in this video frame. So a particular point in the frame, and the third number in the triplet indicates a radius. So if we take those 9 numbers and turn them into a phenotype, the phenotype is 3 differently sized circles that are dropped at 3 different positions into the video frame. So far, so good? There's a lot of seemingly odd details in this experiment, but trust me, there's a reason for this. At the moment, when you're looking at me, or you're looking at the slide, or you're looking down at the desk, it feels like you're getting a more or less, maybe not 360 degree, but you're getting a pretty good panoramic view of everything at the front of this room, right? That's how it feels at the moment. Thinking about thinking is misleading. That is absolutely not what you're actually getting. At the back of your eye, you have a very small region on which light is being focused. So it might not feel like it, but most of the time, actually all of the time, what you're getting is this. You're getting a very focused small bit of your visual field. That's known as your fovea, the focused part of your eye. That's what they're simulating here. But in this case, the researchers are allowing evolution to drop 3 fovea, these 3 circles. All of the pixels in the video frame that are outside of these 3 fovea, that data is thrown away. So far, so good? Okay. So we have these 3 circles, and for each circle, at every 10th of a second, for each new video frame, there's some code that takes the value of all of the pixels inside one of these fovea and takes the average brightness of the pixels inside that fovea. So they're also throwing away color, they're throwing away detail, shape, lines, cross-hatching, all the other detail that might have been captured by these pixels, and reducing everything that's inside that single fovea to a single number. What's the average brightness of the pixels inside that fovea? So far, so good? Okay, so for a given snapshot from the camera, they're going to get back 3 numbers from these 3 fovea, the average brightness inside of these 3 fovea. Those are sensors 5, 6, and 7.
So it can basically look around within its visual field. It can decide what to look at.
It can decide. Actually, it's the genotype that decides. The genotype contains a bunch of synaptic weights and 9 numbers. Okay. So the genotype is encoding where the fovea are.
Where your eyes actually are. It's not
where your eyes are going to focus. In us, we have one fovea, which is at the back of your eye. Who decided to place our fovea at that particular place in our eyes? An evolutionary process. For our ancestors, and luckily still for us, it makes sense to focus on the back of your eye, which means focusing on exactly what your eye is pointed at, not something up here, right? Same idea here. They're going to evolve foci, focusing points inside their visual field, and the gantry robot is going to ignore everything else. So this is a little confusing. Let's try and put some of this stuff together. We've got these 2 trolleys moving back and forth along the table, which means the inverted periscope under the table is moving about in 2-dimensional space, but the periscope is not rotating, so luckily the cable doesn't get snarled. The camera is spinning the dental mirror. It's taking a picture, throwing all of that spinning and all that material away, and at every point in time, it's just getting 3 numbers. What's the average brightness of the pixels there, there, and there at every 1/10 of a second? A different genotype, a different brain for the robot with these sets of synaptic weights might encode a different placement and size of the 3 fovea. So evolution can evolve the ability to look at or focus on different parts of the robot's visual field. Again, some of these details still seem strange why they did this. We'll see why in a moment. So far, so good? Okay, so we've got 7 sensors. We've got 2 motors. How many total synaptic weights does the genotype need to encode? As always, they're going to wire up every sensor neuron to every motor neuron. How many synapses? 14, right? So each of the 7 sensors has 2 outgoing synapses. 7 times 2 is 14. In every genotype, we've got 14 synaptic weights, plus an additional 9 numbers that encode the fovea. 14 plus 9 is 23. In the genotype, it's a vector of 23 numbers. Okay. All right, here we go. Here's the evolutionary algorithm. They started with a particular way of evolving these sets of 23 numbers. They evolved the gantry robot to do something simple, and then once it evolved the ability to do something simple, they changed the fitness function to select for or evolve for a more complicated, more difficult behavior. Once the gantry robot evolved to do this more complicated task, they replaced that fitness function with a yet more difficult fitness function. Sound familiar? We've seen this before. Where did we see this before? Scaffolding. This is scaffolding. I showed you an example of this right back at the beginning of the course with the robot that was lifting that blue block onto its back. When it evolved the ability to do that, we made a change which made things more difficult. In that experiment, we changed the environment. In this experiment, we're going to change the fitness function. Okay. This first fitness function, what they're going to do is they're going to take those 23 weights, download it onto the gantry robot, and they're going to want to see that the gantry robot drives towards the back wall from some random initial position under the table. They're going to then send a command that sends the gantry robot to some other random position under the table. And they're going to evaluate that same set of 23 numbers, that same genotype again. So they're going to assess the fitness of one genotype multiple times. And they're going to take the average of the behavior of the gantry robot for that set of 14 synaptic weights, plus the 9 numbers that encode the 3 fovea. And in this first case, they want to see that for random positions, the robot always drives towards the back wall. They made this task a little bit easier for the gantry robot. They placed a big black rectangle underneath the back 2 struts of the table. So it's got something to sort of look at and evolve the ability to go towards. Go towards the big black rectangle underneath the table. So far, so good? Okay. It didn't take them long to evolve a set of 23 numbers that when downloaded onto the gantry robot, no matter where the gantry robot started, it would always drive the inverted periscope to the back wall. Not that difficult. Then, once they got that, they continued evolving this population of length 23 vectors, but now they changed the fitness function so that every time they set the initial position of the gantry robot, they placed a black rectangle either at the back left of the table or at the back right of the table. And the robot had to drive to the rectangle. Not that difficult, a little bit more difficult. Finally, once the gantry robot evolved a set of 23 numbers, that when those 23 numbers were downloaded onto the gantry robot, it would always drive towards the back rectangle, no matter where it was placed underneath the back part of the table. So far, so good? Okay. Once they got that, they replaced that fitness function with another fitness function that the fitness function that's selected for the following behavior. The gantry robot was set again to some random position underneath the table, and they would place a black square back left and a triangle back right, and the robot should drive away from the rectangle and go to the triangle. Then they'd reset the gantry robot to some random position, and they'd swap the positions of the rectangle and the triangle. Now the triangle was placed back left, and the rectangle was placed back right. The robot should do the same thing. Avoid the rectangle and drive to the triangle. Doesn't sound that difficult. I would normally go through the fitness functions. I'm not going to do that in the interest of time because I want to finish this lecture today. Have a go at trying to come up with these 3 fitness functions. This is optional homework. I want to end with this slide today. Like we saw with the little Kepler robot racing around inside the maze, here's a visualization of the best set of 23 numbers that the evolutionary algorithm produced, again, after 2 or 3 days of running on the gantry robot. So during those 3 days, the evolutionary algorithm tried out hundreds or thousands of genotypes on the gantry robot, and the gantry robot did whatever those 23 numbers caused it to do over and over and over again, until eventually they got a set of 23 numbers or a genotype that caused the robot to produce this phenotype, this behavior. Okay, how do we parse this figure? We're looking down from above through the table. In this case, the rectangle has been placed in the back left part of the table. The triangle has been placed at the back right. They commanded the gantry robot to move to this random position in the horizontal plane of the table. The gantry robot starts to move like this, describes a 180, hits the front edge of the table, and starts to then move in this direction and eventually ends up right in front of the triangle. So far, so good? Same set of 23 numbers. They kept those 23 numbers. They commanded the gantry robot to now move to this initial position. And in this case, the gantry robot drove more or less directly to the triangle. They reset the gantry robot to a third random initial position. It did this. They commanded the gantry robot to move to a fourth and final initial position, and the gantry robot moved with this crazy corkscrew behavior until eventually straightening out and heading directly to the triangle. It's not shown here, but if they swapped the shapes underneath the table and evaluated the gantry robot again with that set of 23 numbers, it would do something like this, but it would drive directly to the back left part of the table and stop directly in front of the triangle. So far, so good? Okay, we got 3 minutes left. Perfect. Here we go. So it looks like when we're looking at the behavior of this gantry robot that it can now distinguish between triangles and rectangles. Again, it's not going to win any Nobel Prize for this, not the most difficult task to perform, but presumably this robot can distinguish between triangles and rectangles. Yeah? How? How does it distinguish between triangles and rectangles? Deep breath. Let's go and plunge into the brain of this gantry robot and see if we can figure out how it's doing it. It turns out that the genotype that produces this behavior actually doesn't use the third fovea. It actually makes the radius of that fovea 0. The evolutionary algorithm is kind of showing off. It says, I don't even need 3 fovea. I just need this one and this one. It also says, I don't need the bump sensors because there's nothing for me to bump into. There's nothing underneath the table. So what happens is, although there are seven sensor neurons, only 2 of the 7 sensor neurons have synapses that connect from those sensor neurons eventually on to the 2 motors. There's actually 3 outputs here. We'll just ignore this detail for now. So this particular genome is only using 2 of the 7 sensors to drive the behavior of the gantry robot. So far, so good? Okay. Where is the recognized triangle neural component in here? Where is the recognized rectangle neural component in here? I see some of you shaking your heads. Good. I know I repeat myself. Thinking about thinking is misleading. This robot can clearly distinguish between triangles and rectangles. It has no recognized triangle component and recognized rectangle component. As you might see that there are synapses that are pointing from the left to the right that are sending sensory information down to the motors, but there are also some self and recurrent connections. What do recurrent connections do in a neural network?
Build memory.
They provide memory. This gantry robot can remember things, okay? Let's have a look at these 2 fovea. As the robot is moving around and describing a curved trajectory, these 2 fovea come and they hit the left side of the black rectangle. As they hit it, the top left fovea goes dark, and then as the robot is driving in this curved trajectory, a short time later, this fovea goes dark. Everybody see that? So if I'm looking just through these 2 fovea, and there's a black rectangle on the wall back there, this one goes dark, and now this one goes dark. Or better yet, this one goes dark, then this one goes dark. That's what the gantry robot is seeing. As it continues moving, these fovea sweep over this triangle as well. This fovea goes dark, then this fovea goes dark. How does the robot distinguish between triangles and rectangles?
There's a difference in like how long it takes for them to go dark.
There's a difference in the timing between fovea 1 going dark and fovea 2 going dark. We're going to end today with arguably my favorite slide in the entire course. This is embodied cognition. This thing can distinguish between objects and its environment, and the way in which it distinguishes is a function of how it moves, what it sees, what it thinks, what it remembers. It's combining space, time, movement, sensation, action in a particular way that allows it to recognize, distinguish between objects with a tiny, tiny, tiny brain. There are 10, 12 synapses here. Easy peasy. A computer graphics algorithm or a deep neural network can also distinguish between triangles and rectangles with way more synapses and more mental effort. Embodied cognition wins. You have a quiz due tonight. Undergraduates, you're working on assignment 5. Grads, you're working on 9 and 10. See you Thursday morning.